Greetings, chemistry students. Today I'm going to introduce you to a concept called chemical equilibrium, which is a really key concept in chemistry. You may be familiar with the term equilibrium re- as it relates to the term balance, like your sense of balance is determined by your sense of equilibrium, which is determined by, um, oddly enough, your inner ear maintains your sense of balance. Well, chemical equilibrium is also kind of like a sense of balance in chemical reactions. And so the way this works is chemical equilibrium applies to what are called reversible reactions. So that's a reaction that not only can it go from reactants to products, but the products can go back and reform the reactants. And so, for a reversible reaction, when the rate at which the forward reaction and the reverse reactions are identical, you have reached what we call chemical equilibrium. This does not necessarily mean that the concentrations or the amounts of your reactants and products are the same. It just means that the rate at which you are forming products and forming reactants are equal. And each chemical reaction proceeds to an equilibrium state that is described by the equilibrium constant K, specifically the capital letter K. And they use that because in German, which used to be the language of chemistry, the word constant is spelled with a K. So equilibrium constant is spelled with it's represented by the capital letter K. So we're going to look at a little simulation here to kind of help you understand chemical equilibrium. I have this reversible reaction where substance A can turn into substance B. And right now, all I have is substance A. So substance A can turn into substance B. So the forward reaction can happen, but the reverse reaction is not possible right now. You can also see that this is an endothermic reaction as it proceeds. So, as we start this, some of these molecules of A will start turning into molecules of B. But until you form some Bs, you can't have any reverse the other way. Now, we've just had two molecules reverse this reaction now. So, the rate at which the reaction is going backwards has increased. Eventually, we'll reach a point where the rate at which A's turn into B's and that B's turn into A's will be equal. And that's when we have reached chemical equilibrium. Now, we're about at that point now, as for every one that crosses one way, another molecule on average will cross the other way. So the amount of A's and B's will remain relatively constant. So that's just an example of the chemical equilibrium process. Now, with chemical equilibrium, we can write what's called an equilibrium expression. So, for a hypothetical reaction, A plus B makes C plus D, where the lowercase a's, b's, c's, and d's are the coefficients, this is how you would write the equilibrium expression. Now, the square brackets represent concentrations or molarities, if you will. And so the molarity of C raised to the power of its coefficient times the molarity of D to the power of its coefficient, these are your products, divided by the concentrations of your reactants raised to the power of their coefficients equals your equilibrium constant. Once equilibrium is established, these things will be equal. And the larger the value of K, the further to completion this reaction goes, which should make sense because the larger the value of K, that means you're going to have more products, more things in the numerator, and less reactants, fewer things that are in the denominator. So if K is a very large number, that means when equilibrium is established, you have a lot of C and D and very little A and B. Now, the other thing about K is even though it's an equilibrium constant, it does change with temperature. So let's consider one of the most important chemical reactions that's ever been discovered and manipulated in chemistry, which is the reaction of nitrogen gas plus hydrogen gas to make ammonia gas. Now let me balance this up. Now at 500 degrees Celsius, K equals 0.06. So that's the equilibrium constant. That's a relatively small number. So that means that at equilibrium, we have a lot of N2 and H2 and very little NH3. We can also write an equilibrium expression. That would say that K equals, now it's products over reactants. So it's going to be the concentration of NH3 squared over the concentration of N2. And now the coefficient was a 1, so we typically don't write things raised to the first power, times the concentration of H2 cubed. So that's what the equilibrium expression says. And so no matter how much of each of these things we start with, the reaction will adjust so that at 500 degrees Celsius, the molarity of NH3 squared divided by the molarity of N2 times H2 cubed equals 0.06. So if we started with a whole bunch of NH3, then this reaction would run backwards to produce more N2 and H2 until these ratios equal 0.06. And if we started with entirely reactants, then the reaction would proceed forward just a little bit until we made enough product that this expression equals 0.06. At different temperatures, this would equal different numbers. There are some other reactions that we could consider. For instance, there's the reaction hydrogen gas plus oxygen gas makes water vapor. If we wrote an equilibrium expression for this, K would equal the concentration of H2O squared over the concentration of hydrogen squared times the concentration of oxygen. And we're going to look at one more example, which is the reaction of nitrogen dioxide. Now, I should have written these with double arrows before. Nitrogen dioxide makes dinitrogen tetroxide. For this one, nitrogen dioxide is a brown gas, and dinitrogen tetroxide is a colorless gas. The equilibrium expression says that K equals the concentration of N2O4 divided by the concentration of NO2 squared. So if you could write an equilibrium expression and have a basic understanding that if K is very large, that at equilibrium you'll have a lot of products, and if K is very small, you'll have a lot of reactants, you've got the basic understanding of this down. I'm also going to show you a quick demonstration with this reaction to show you how K is changing with temperature. So stay tuned for that, and then I'll have an assignment for you to do. So have a great day. All right, for this demonstration, I have a flask that contains nitrogen dioxide gas in equilibrium with dinitrogen tetroxide gas. So NO2 can combine to make N2O4. And I can adjust the equilibrium position by changing the temperature, because nitrogen dioxide has a brown color associated with it, whereas dinitrogen tetroxide is colorless. So if I take this flask, and you can kind of see what the color looks like, and I submerge it into some warm water, what you should notice is that the color will gradually change, and the contents of the flask will become darker in color, because this is shifting the equilibrium position to produce more nitrogen dioxide gas and less dinitrogen tetroxide. So it's shifting it more towards the brown side. You can see it has become a darker brown color. If I then take this flask and submerge it into some cold water, we should notice that the contents of this flask will become lighter in color as it shifts the equilibrium away from the nitrogen dioxide and towards the dinitrogen tetroxide. And so you can see right there that the flask has become a lighter brown color as we've produced less nitrogen dioxide. We've just shifted the equilibrium position in the other direction.